So I'll try to say in today's lecture and tomorrow's a succinct version of what I had planned for 3 lectures. And I'll remind you again of the systems, and I'll try to, at Dov's instruction, try to say a little bit more about the kind of phenomena that we're really interested in, okay? Then I'll outline the framework in a slightly simpler form. I'll say a little bit about entropy production, and I think today's lecture will end with that. In tomorrow's lecture, I'll rather differently present some current work on phase transitions in active systems, which will illustrate to some degree some principles of StatMech out of equilibrium and how they apply in these systems. Okay, so I mean, I don't want to show you this. Well, you know, it was there, yeah, just for fun. I mean, ultimately, we are interested in ordering phenomena in systems in which the individual degrees of freedom are driven far from equilibrium. Probably the simplest system in which you see a really striking ordering phenomenon is not flocking of particles that have an orientation. Imagine you just have a bunch of particles, each of which is carrying a little arrow saying, go that way at a certain speed, okay? And you have a few more particles like that. And, imagine you just throw them into a system. And you let the system go. And imagine what you have is that each of these arrows is which way the particle is pointing. And so each particle is endowed with a speed v0, and this arrow is also doing rotational diffusion. So if you think of the arrow as making an angle theta with respect to an arbitrary reference direction, then theta is executing rotational diffusion. So what this means is that there's a time which is 1 over that constant dr, and in that time, that particle forgets which way it's pointing. So orientation correlation time. Okay. And let's say these particles have a size. So they're hard disks. They follow their nose. They don't have any interaction with each other other than excluding each other. They don't care to align with each other. And this picture probably from these guys' work, shows the remarkable behavior they display. These are ordinary hard disks without self-propulsion, non-motile, at low concentration and at high concentration. And at the same low concentration and the same high concentration, these are these particles, the ones that are following their nose. And what you see is that simply because they can't get out of each other's way, they can't go through each other, they can't get out of each other's way by seeing each other and avoiding each other, and it takes them time to turn around in order to get out of each other. Their only way out is to turn around. You get this. And now, this isn't some sort of transient phenomenon. This is an honest-to-God phase transition. It's actually condensation. It could be vapor-liquid or vapor-solid. Okay? So that's one class of phenomena which, yeah. Yeah, you can. So, clearly, which part is in the condensed, which is not, there's this sort of lever rule or whatever it is. Yeah, that's standard. So, I mean, the point, if you like, is that although there are differences of detail, this is actually more or less like the vapor-liquid transition. Right. So one of the reasons I mentioned it was that, there are two ways of now trying to understand this. One is you write down either a particle-based or a continuum field theory of this problem. And then you say, okay, we are not in an equilibrium system. So you introduce some things that wouldn't have been allowed in equilibrium and see how they change the field, the theory of condensation that you know at equilibrium. What Dov did, I guess, towards the end of today's lecture, right? Yeah, which I wasn't here for, is to show that there are other signatures that tell you about the nature of this phase transition. So here is one kind of phase transition in systems that eventually, not necessarily in my lectures, but eventually we'd like to understand, and on which much progress has been made in the active matter game. Another kind of system is where instead of now particles that are just round and isotropically repelling each other, imagine the particles themselves were elongated. Okay? Then, of course, this is overkill because I've not only made them elongated, I've also, and not only made them self-propelled and elongated, we've also put a little trap. You can do this without a trap. So let me first on the board tell you what might happen without a trap. So imagine now that you have these same particles and, accidentally they condense into some region like this. But now these things are elongated. So it's going to be harder for them to get out. If you had these disks condensing into some region and pointing like this, each disk is still pretty much, even in the condensed state, is pretty much free to turn around, unless you start introducing complications like static friction or something. Okay? So these guys can escape. These guys are much more effectively trapped. So one problem that we've been studying is an analog of this condensation of self-propelled particles, where you put in a permanent obstacle in the way. And then what you find is there is a phase transition in which if the angle of the wedge is small enough, the particles don't escape. I should mention that this is from, the original idea is from, I don't remember all the authors, but Hartmut Leuwen's group, sort of Brownian dynamic studies, first pointed this out. It's closely related to another class of phenomena, which I won't really talk about, which is, imagine you have a structure like this. Is this big enough? So I've got a little hole, I've got a big box, I've got a wedge, another wedge, and you've got holes here. And you start out these self-propelled particles running around all over the place here. If these had been equilibrium Brownian particles, the obstacle would have introduced some minor structuration in its own vicinity, but on average, the particles would be spread everywhere. The particles would do more or less what they're doing without the obstacles. In this case, what ends up happening is, it's like Roach motels. The particles find it easy. How many of you know about Roach motels? Dov knows about Roach motels. They check in, but they find it very hard to check out. Okay? And so you end up getting, imagine this is actually a box with boundaries. Imagine you end up getting everybody eventually on this side. So what ends up happening is that, see, there is clearly a local vectorial asymmetry here. That way and this way aren't the same, because this way you go through a hole, that way you run into a block. Okay? So this region is characterized by a local asymmetry. And given enough time, what ends up happening is the particles all get affected by that vectorial asymmetry and accumulate on one side. This I will say something about. And why am I talking about this in an entropy school? The reason really is that the analog of trying to cash in on entropy is that each of these particles is turning around at random. And on long length scales, that turning around at random is more or less like diffusion. And so the competition is between the tendency of particles to go in the manner in which they're directed and the tendency of particles to cash in on something like a positional entropy and explore space more fully. And what ends up happening is that if the angle is small enough and if the ambient concentration of particles is large enough, you end up getting this condensation here, you end up getting an accumulation here. So these are experiments in Ajay Sood's group, done mainly by Nitin Kumar. Of course, unsurprisingly, you can simulate these, because if you imitate the experiment carefully enough, you can simulate them, but you can, of course, play with other parameters. The nice thing is, in the next lecture, I'll tell you a little bit about a theory of why this happens. Whether that belongs really closely in this school is not obvious, but it's an interesting story, so I'll tell you about it. Another interesting class of phenomena is this. Now, Remember I said that if you have any kind of vector asymmetry at the level of the particles, so if you've got a particle with any kind of shape asymmetry like this, and so plus activity, I'll try to make much more precise today what we mean, but basically time reversal invariant broken at the level of the particle implies a velocity. Okay? Now, imagine a system made of particles which don't have that asymmetry. The system here is a collection of rods, macroscopic rods, on a surface, which I talked about last time. Each individual particle is the same on both sides. Okay? So if you have an aligned phase of these guys, so imagine you take a system of this sort and you put in more and more particles, and this system is vibrating, so these particles are sort of doing some kind of random motion, they're jostling each other. And not surprisingly, at large enough concentration, you do find an aligned state. Okay? It's an aligned state, but unlike a flock, it's an aligned state in which the particles, on average, aren't anywhere. Right? However, if I have that slide here. Not sure why I don't have that slide here. Just give me a second. I'll talk about this more in the next lecture. But what I just wanted to say here was, when you have objects like this, you can ask what kind of topological defects can this system have? Topological defects are like charges. They're places in which this orientation goes through a full symmetry as you go around a little point. The symmetry here is under pi rotation. So the defects are ones which, as you go around a point, either go from pointing this way to pointing that way, pointing. Let me put a little dot at the tip just to keep track. Okay, what have I done? That, and it comes back, it's pointing this way. But remember that dot is just a marker for my keeping track. What's happening is that the orientation has gone from pointing this way here, maybe pointing that way here. So the orientation has gone like that. That's one kind of defect. The other kind of defect is where, as you go around a point, you go from pointing like this to like that, like that, and like that. So here what's happened is you've gone through minus pi. Here you've gone through plus pi. Now if you look at the structure around this, it's like it's pointing this way here. So it's roughly 3/4 symmetric. And you can see examples of both these guys up here. If you look very closely, you will see an example of this kind of object over here, and here an example of this kind of object. I argued that anytime you have any kind of vectorial asymmetry, you should get motion. So if you look up here, and if you have an object that's symmetrical, it might sort of rock around at random, but doesn't in fact know which way to go. So what you expect is that these guys, on average, won't move, and these guys will move. So what happens is that the topological defects of one kind themselves become self-propelled particles. So what we'd like to understand is, and this is absolutely a result of the combined effect of vectorial asymmetry and broken time reversal. So what we'd like to understand, and I'll say a little bit about it in the next lecture, is what does this do to the well-known theories of the disordering of ordered phases by the production of topological defects? We'll see that it does something very interesting. And I mean, just to show you what these guys do, that they really are traveling objects. can actually see the plus half moving and the minus half sitting there. Again, just as a reminder that physics is actually about experiments, this is experimental measurements. These are not simulations, yes. Minus half at the following level, that all I can say is, if you have a vectorial asymmetry, something that tells you my nose is pointing in that direction, front forward is that way, then in general I have no choice but to move in a direction dictated by the asymmetry if I'm not at equilibrium. If you look at the minus half, it's got a roughly equilateral triangle kind of structure. It's structurally threefold symmetric. It doesn't have one direction in which to move. And therefore, of course, it'll move around a little bit at random. It'll move around by being induced to move by other things around them. But a minus half far from a plus half will not. Because it doesn't carry a vector saying that way. I think this is all probably I wanted to say at this stage. Okay, so those are reasonably precise motivational remarks. What I want to do, of course, is to build this. I already talked about last time. One point I wanted to make before I go further. Remember that again. As students, the kind of StatMech you've done is all about the systems up here. Either you have truly closed systems, or a part of a closed system. Let's say this is the part that I'm talking about, and this is the rest of it. You either study systems of this sort, or you study systems of this sort coupled to the rest, and this guy plus the subsystem plus the path is closed. And in these two systems, you know how to do statistical physics because you've learned equilibrium statistical physics, you've learned about the postulate of equal a priori probabilities. And the physics of these systems is invariant under time going to minus time. The systems that we'll talk about in my lectures, what's left of them, are systems in which you don't maintain them at a constant energy budget or even at a constant energy budget plus minus a little bit, which is temperature, but you maintain them at a constant throughput of energy. You have to go on pumping the system in order for it to do what it does. Okay? So the kind of motion we're talking about is not the kind of motion we call heat, it's something else. And in particular, these are systems in which you've broken time reversal, as I said. And so we are trying to invent the rules of those systems. So just to set the stage, I'll remind you again, we'll try to build the equations of motion in this picture, where what you have is, think of this as the following. Imagine you have one motor car, or motor protein, doesn't matter, sitting on a track or a road. It consumes fuel. What is consumed? So it moves, its chemical coordinate moves up in that direction, which means it keeps eating fuel, either onboard fuel or it lives in an abundant environment and takes that fuel and consumes it. You drive it in that direction. What do I mean by drive it in that direction? What I mean is I make sure that on average, the fuel tank is maintained at the same level. Okay, so it's consuming fuel, I keep topping it up. And if I do that, I'll keep going that way, and the systems that are of interest to me is where the chemistry or the driving in that direction is internally coupled to the spatial part of the mechanics. In actually chemical systems, that driving force is the chemical potential difference between the chemical reactants and the chemical products. Right? Delta mu, chemical potential is the thing that tells you on average how much of something a system wants to have. And if you maintain this difference, it's like telling the chemical reaction, keep going that way. Okay. Now, our aim is the aim of today's lecture among the aims of this language is the following, that often people take systems far from equilibrium and on very general grounds say, terms like this are allowed. I mean, for example, I have an interface, let us say, and let's say it's an interface which for some reason lacks up-down symmetry. There's either the objects on the media on the two sides are different, Okay? If the system were at thermal equilibrium, then even if this is an interface between two dissimilar objects, the mere existence of a vector that points, let us say, from oil to water will not make the interface start moving in that direction. Just like the mere existence of a vector like this at a single particle level at equilibrium doesn't make the system go that way. So in these systems, what people do is they say that if you're not at equilibrium, then you say, look, I'm going to write down all terms that are allowed because I'm no longer constrained by what I can do at equilibrium. So, for example, I will say that if H is the height field of the interface, and imagine the interface is governed by some energy function which is a surface tension times the area of the interface. So I've got a system in d dimensions. In d minus one of them lives the interface. The area, as you all know, is given by that. And this tells you the area and the energy cost of having an interface like that. So you will say, okay, friction times h dot should be equal to derivative of h with respect to little h plus noise. That would be the equilibrium dynamics. Okay. What am I doing here? I'm doing the same thing that you do with one particle with damping and a potential and no inertia, and saying damping times velocity is equal to force plus noise. We understood from last lecture how to write down the noise. And then what we'll say is if you're not at equilibrium, I should be able to add other terms. What is the simplest other term I can add? Well, there's a vectorial asymmetry. Therefore, I should be able to introduce just a constant, right? Or let me write this differently. I've done two things wrong here. I haven't put a minus sign where I should have. And let me write it this way, minus 1 over zeta. So now this becomes a velocity rather than a force. And so do you understand the point here? That is that if A and B are different, and I'm in a homogeneously driven state, then all of a sudden I'm allowed to put in a term of this form. Okay. What else can I do? I'm allowed to put in terms. Remember, I'm liberated from h going to minus h invariance. I'm clearly allowed to put in terms of the form grad h squared. I'm also allowed to put in terms of the sort that are already allowed, meaning that I can put in terms of the sort that would have come from differentiating this, right? So am I making sense, Mr. Levine? Right? So just as a simple example of pure thought, pure unaided reason modeling, it says, got a system like this, vectorial asymmetry, I can write down an equation of motion like this. So one of the things I'd like to explain today is how you might understand this by saying what I have really is an interface coupled to a chemistry of some sort. And I'll show how it's kind of natural that these terms come up. You could, of course, argue that it's already natural because, if you were trained, as I was, to say that, look, I'll write down whatever is allowed, it's natural anyway. But it's kind of nice to see how you can relate this to the framework that I talked about. Okay? All right. So I just mentioned that to say that it's a way of understanding in a slightly new language the idea that you can put down quote-unquote new terms, terms that you couldn't write down at equilibrium. Oh, I can just look at that right here. I think, okay, let me use the next 2 slides or so to rediscuss the same point. So the way we were proceeding, and I'm reiterating this last time, is now let's not even think about chemistry. Imagine you have a complicated phase space with coordinates qp and coordinates big X, big pi. I apologize for complete inconsistency of notation during last lecture, between last lecture and this lecture, and during this lecture in advance, and in future, and next lecture. Okay? So now you see, we are out of equilibrium, so all rules are relaxed. All right. So now, if you were just writing down Hamiltonian dynamics, then what you would say is Q dot is dH over dP, X dot is dH over d pi, P dot will have the force due to Q, the other momentum dot will have its force. Now I introduce damping. And today I'm expressing this in a slightly different language from which I did last time. The idea is the following, that I make the damping cross-coupled. The idea is the following, that I say that a velocity of one variable sort of entrains the velocity of another variable. It's rather as though, I'm blowing, I've got some object here, I run a continuous current of air at it, and as a result of a coupling of the frictions, this flow drives that guy. Okay? So you can think of this as one velocity, the velocity of the other variable. So first of all, there's a damping on P for the usual reasons, a purely diagonal bit. There's a damping on the other variable for the usual reasons. And now you say that there's going to be a damping on P due to the other velocity and a drag on pi due to that velocity. Okay? And there are these coefficients here, and what you will have learned or should have learned in time-dependent StatMech, and right now I'll just make it an assertion, is that gamma 1, 2 is equal to gamma 2, 1. But to make this whole story interesting, the one crucial ingredient I have to introduce is that this off-diagonal kinetic coefficient should depend on some dynamically variable of interest. Okay? So then I say, okay, now let me think about the case where x is actually a chemical coordinate. I don't want to ask myself what I mean by the momentum conjugate to the number of fuel molecules consumed, so I'll just rub that out. I can probably contrive a way of saying it, but I won't. So now I have an equation of motion in which I can eliminate the chemical velocity from the momentum equation by taking this equation and solving for that chemical velocity in favor of the chemical force, the physical velocity, and the noise. Okay? Those of you who actually kept track of my somewhat less organized remarks yesterday may find this a repetition, but so the idea is the following. Basically, this guy is just the chemical velocity. I take the dynamical equation for the chemistry and eliminate this guy from this. The result will be that this equation will get modified, both by changing the original damping term, not both, by changing the original damping term because of a contribution from here, by changing the noise because of a contribution from here, and by giving you one term that's proportional to the chemical driving force and this off-diagonal guy. Okay? So when you do that, when you replace the chemical velocity by chemical force, etc., you get a pair of equations of motion for the coordinate and the momentum. Nothing has happened to the coordinate equation. The momentum equation has got interestingly changed. You've got a new damping because of a contribution from the other variable. You've got a new noise because of a contribution from the other noise. And you've got this term. Right now, I'm entitled to do this, ignoring inertia of the other variable, I'm entitled to do this even for the equilibrium problem. So at the moment, this is just the equilibrium dynamics of little q, little p, and big X. And it's not specific to the case where you have to think of X as a chemical coordinate. It's just another variable. Okay, it could be you're driving some other thing through it. But the end result is that you can now say, okay, I'll take that chemical variable and I'll hold the force on it at a fixed constant value. Right? Remember, thermal equilibrium is where all average forces are zero. Right? That's one way of stating it. The fact that you're holding this fourth non-zero value means that this equation now has acquired a term proportional to the chemical force, in general, depending on the other coordinates, and I've allowed it to depend on Q. And you will say, well, this is no different from allowing terms in the equation of motion that are symmetry permitted. And it's true. Okay? But places it in a Langevin equation context. So what we have is a modified Langevin equation. Now, of course, we've made several fairly grave assumptions here. basically, because we are working in a spirit of linear response, we've assumed that even when I hold delta mu at a non-zero value, nothing else changes. The noise doesn't change. Okay? So you can say that, is that general enough? It's not general enough, but it turns out that it induces complete generality to the form of the equations of motion as far as the deterministic terms go. So the end result of this analysis, and Q could be any number of components, P could be any number of components, is you get a dynamics in which you get a new position dependence. Now, obviously, if you're, okay, so actually, if you take this pair of equations, you can say, well, if that's just some function of Q, why can't I redefine the energy function? Right? I've got P dot plus blah, blah, plus this. I can just change that. The reason I can't, in this simple one variable problem, you probably can redefine the energy function because as long as P and Q aren't coupled, which they shouldn't be, it won't change the Q equation anyway. So at this level of analysis for one coordinate and one momentum, this is not really very dramatic. It just says you move things around. So what it means is that the energy function isn't the object you thought it was. And so you could still get an equilibrium description. The moment it's more than one component, then given that this term has to be the gradient of H with respect to Q, if this guy is non-potential, then immediately you can't write it as a modified energy function. You can also go down further. You can say, okay, let's take this problem, and now let's throw away inertia. We're looking at very tiny particles moving slowly in potentials that aren't varying very rapidly. So I'll throw away P dot, and I'll just replace dH over dP here by Q dot, and then I'll get an equation for Q alone. Okay? And so what do I get? I get Q obeys its original equilibrium type dynamics with a noise and a damping that agree, and it's sprouted this extra term. This extra term is in the spirit of the terms that you wrote down to write the KPZ equation for the interface. Basically, you can put into gamma 1, 2, whatever the symmetries, the spatial symmetries of the system allow. In particular, gamma 1, if Q was that interface height variable, this term could have constants, it could have grad H squared, and it could have terms that already come from the energy function. In other words, it could have terms of the same form as those that come from here, but it could have other weird terms. So if you like, this is a post facto justification for invoking this general principle that once you're out of equilibrium, once you lose time reversal invariance, all you have to do is to respect the spatial symmetries of the problem, and you can pretty much do what you want. But it's enlightening because it tells you how it's coupled to the dynamics of the variables that you're not looking at. Because clearly behind this dynamics, the chemical dynamics is still going on. Okay? On average, that chemical dynamics is just chemical velocity is equal to a mobility times the chemical driving force, plus fluctuations. Right? That's all that X is doing. But, all right. So, yeah. So as I said, for example, if Q was the height field of an interface, you will get this equation. Imagine a slightly more complicated case where Q and big Q are the center of mass and relative coordinate of a timer. Then carrying out the same set of stunts and allowing the off-diagonal kinetic coefficient to depend on the relative coordinate here, you can get an equation of motion for the center of mass, which gets driven at a rate determined by the extension. That extension variable has its own dynamics in its potential. And depending on what you put in here, you get the cases that I discussed last time. If Q has a preferred length, then you get something that's more or less like a rigid timer propelling itself. If Q is quadratic, you get the other example I talked about of a timer with, which sort of, whose extension hangs about around 0, but tends to point in a given direction and therefore goes in a given direction for a while. Okay. So you can get both the active Brownian particle and the active Ornstein-Uhlenbeck particle, two things that the Cambridge group has discussed a lot. The only thing is when you do this, what you get, so now this is looking a little hairy, but what you should note is the following. You get in the little q equation, center of mass equation, you get this variable. And if you think of this dynamics of q, so if you think of the case where h, supposing h is the entry of q into h is just of this form, then you'll get q dot plus 1 over gamma 1 1 k q equals naught. Okay. So this means that q has correlations that decay exponentially in time with a time constant which is gamma 1 1 over k, right? So you can say that I'll not even look at the q equation. I'll just, supposing I take a very simple case of gamma 1 2 being just proportional to q. Then it's as though capital Q enters the little q equation as a kind of noise with time correlations on a time scale tau. So capital Q what is called a colored noise. For those of you who aren't familiar with this terminology, when a noise's spectrum is, when a noise is all frequencies equally represented, you call it white. That means its time correlations have zero, are delta correlated. Because that's called white, the moment its spectral content varies with frequency, you call it colored. Yes? Right. 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 So, okay. So, this is actually the same example. So, let me just say exactly what I mean. In this general framework, I'm doing something that's slightly more restrictive than needs to be done. I'm still assuming the noise terms. I don't have to. I'm saying the moment I introduce, okay, this dynamics at the moment in this form is equilibrium dynamics. Okay. If I declare delta mu to be held at a non-zero constant value, what I'm doing is I'm taking one of the forces in the problem and declaring its mean to be non-zero. The moment I declare any mean force to be non-zero, I'm out of equilibrium. Strictly speaking, I should relax the relations between this noise and that guy, and the noises and the dampings. But at this level of derivation, I haven't asked what happens to the noisy part of the dynamics. See, I mean, for example, let's take an extreme case. Supposing it wasn't molecular and colloidal scale chemistry going on, but my horrible, noisy, vibrating plate. Delta mu there is a little hard to define. All I can say is each shake is one sort of consumption of a unit of energy in some form. The noise there is totally, I have to model it completely phenomenologically. So what I'm doing is I'm pretending that even when I put on a strong chemical driving, nothing else happens. So I'm using the equilibrium system as a reference system. I'm assuming, therefore, remember, the only reason those noises had the relation they had was because I want to be at thermal equilibrium. So what I'm doing is I'm not worrying about what strong chemical driving does to the noises. That's what it is. But the problem won't be equilibrium anymore, because the moment you declare this thing to be non-zero constant by hand, what I'm saying is that as the chemistry, as one more fuel molecule is consumed, I'm constantly topping up the reactant. Right? Right. That's exactly that. Yeah, so it's exactly the same. The point is, strictly speaking, if you look at the chemical landscape, X, I should think of X as a discrete variable. So in a continuous picture, I should probably do something like, a continuous way of doing that would be to say, this is the energy landscape that X faces, okay, at equilibrium. And then driving means I'm going to tilt this. And so if I took, I'm pretending that this is just dead flat and putting in delta mu just does this. The only thing I'm not resolving the fine structure here, which doesn't matter for our purposes. yeah, so the only thing I wanted to say is that you can, if you ignore the original thermal noises in this equation, and only this is like mass variable in a potential, but driven but driven by a colored noise. So I have a damping without memory, and this guy which is like a colored noise. So clearly it's not an equilibrium problem because the noise correlation has a time decay, the damping is instantaneous, it's local in time. I'll say more about all these things because the remainder, once I get past this bit, is to it makes some difference. It depends on what quantities you want to look at. Yeah. Just like if you were doing an XY model or something, you could have I mean, clearly, if you wanted these things to order, you'd need some interaction which would first form a local moment, and then those local moments will interact with each other and order. But, you could imagine something where the mere fact that something is extended gives it a self-propelling speed, and the interaction, rather than coming from some alignment interaction, if it's actually between the velocities, you could imagine making the ordering physics not depend on a scaling up of a local tendency to form a non-zero Q. So I have to think a little bit about whether I can construct a specific example. Okay. Yeah, so let me just for fun show you an example. So someone sitting over in the back there, Vijay, did this during his PhD. This is a dimer. In this case, the dimer has a slightly more complicated property. The damping on one of the heads of the dimer depends on whether it is stretched, this pair is stretched or not. Okay? So I'm not showing you the equations of motion, I'm just showing you that you have a dimer with a stretch-dependent damping, and you can either give the noises on the dimers a form that respects that stretch dependence, which means the right kind of multiplicative noise to keep it at equilibrium, or you can give it, or you can fail to respect it. And what Vijay is doing here is alternating between having an agreement between the noise and the stretch-dependent damping and not having that agreement. And the moment you don't have that agreement, the mere fact that the dimer has an asymmetry with the stretch dependence makes it propel. If you look at the center of mass velocity, you will, at equilibrium, the velocity is nicely e to the minus v, distribution is Gaussian, and the internal force goes too quickly. The internal force is nicely averaging to 0. You break detail balance by spoiling the relation between noise and damping. The internal force acquires a non-zero mean. The velocity distribution function gets peaked, gets shifted over that way. And then you can also reverse the asymmetry and have a lot of fun. So, because these kinds of phenomena are so cool, we want to make a comprehensive theory of active matter and see what it does. So among the things we'll try to calculate by next lecture is entropy production. The moment you break detail balance, the moment you spoil either the relation between damping and noise or introducing terms through a delta mu, you are in a state which isn't time reversal invariant. You've given everything an arrow of time. So what we'd like to see is how that gives us entropy production. You know that a system at thermal equilibrium is in a state of maximum entropy and the entropy doesn't evolve further. So what we'd like to understand is how in these active systems, the presence of a delta mu gives you an entropy production. So for instance, we'll work out a general expression for the entropy production of one of these guys, and then for the particular case where the particle is moving in a quadratic potential, then I'll construct entropy production in two ways. This is a little hard to explain at this stage. The point is that the definition of entropy production depends on the definition of time reversal. You can imagine reversing time and reversing the little arrow, or you can imagine reversing time and not reversing the arrow. So what you're asking for in one case is the relative probability of the particle moving like this and like this when it's being told, when on average it wants to move that way. And the other case, you're asking about probability of going this way versus going this way. don't think I can't do an animation better than that. And there are nice experimental systems in which some of these things can be studied. And here it is in 4 dimensions, 2 dimensions, and moving through medium of obstacles. So that these are, this is a kind of non-Euclidean statistical mechanics on which you can set up nice experiments at a tabletop level on very, very prosaic materials, little bits of metal and so forth. So I think I'll stop this part of the discussion there. So I guess we can move can somebody put the screen up? Oh, it's happening. I will have to bore you a little bit by telling you elementary things. I'm sure that many of you know these elementary things, but I'm also confident that many of you would benefit from seeing them again. So let me teach you. I made various confident assertions about Langevin, Fokker-Plancle, and mean square displacements and so forth. I want to use that framework to calculate things like entropy production. So what I will do today is to discuss some of that. And I'll try to stay consistent with at least my own notation. Huh? Yeah, not just today. Actually, the real problem is that I usually end up, because I don't look at my notes when teaching, I usually use notation that's inconsistent between the board and the notes. It's fairly fatal to the lecturer. Okay. Now, see, the trouble is this notebook is falling apart, so walking around with it. So let's go back to the problem we know and love. So you have, forget about the notations I used earlier. I'll use Q and P to be the coordinates and momenta. And I just want to re-understand all the way from Langevin equations. So what I want to tell you about a little clearly today is Langevin, Fokker-Plancle, or Kramers, and detail balance, and entropy production. And the idea, I mean, starting point is really that, if you imagine you have a particle moving with some, under the action of an external force, and there's some damping gamma, then you know that at long times, if the velocities are slow, then you get a speed which is the force divided by the friction. And you know, therefore, that you get a power which is the force times the velocity, which is the mobility or the inverse friction times the force squared. Right? So you know that if you hold the particle out of equilibrium by subjecting it to a constant force and driving it in some direction, you dissipate heat at this rate, right? The power dissipated. And that's a measure of entropy production. This doesn't mean that anything interesting happens to the configurations of the system. This is entropy production for the universe as a whole. Yes? Oh, light for the board. Okay. Yeah, so lights. Actually, tell me which is the invisible zone? Now it's okay, right? Better or? So This is readable? Fine, all right. So we'd like to just understand this idea in the context of the systems that we have. So there's a delta mu, which is our driving force, and we want to calculate entropy productions for some simple model systems in this language to understand exactly the sense in which they are out of equilibrium. So to do that, let's first just understand Langevin equations slightly more carefully than we have done. So I'll have Q dot equals P over M. So Q and P are coordinate and momentum. And P dot is equal to, let's say there's an external potential. Let me give it some name. I'll add vector signs and indices and components when I need to, but I'll try to keep it without all of that. And then we say there should be a damping. And there should be a noise. And you know that the reason this was done is that when people observed very small particles, you found that if you had a particle in a fluid medium, you know that if you apply a constant force on it, it settles down to a constant velocity in this manner. And you also know it fluctuates about that. And you know that the damping, it turns out that the nicest way of writing the damping is as a term proportional to the velocity. And then there's a noise. Now, supposing we didn't know how the noise was related to the damping. Supposing we just said there's a noise here, okay? And we say that it is utterly uncorrelated. So that means on average it is 0. And from one time to the next, it's some A into a delta function. Right? And we want to show in very general terms what A has to be. Another version of this problem is where we can ignore inertia. Then what we'll say is that so here you'll have Q dot equals minus 1 over gamma Q prime of Q plus gamma. And what we'd like to know, and we'll do it first in this simple reduced case, what A has to be in order that so for at long times now, there's any number of ways of seeing this, but let's pick one. Let's work it out first for the case where there's no potential. So then you have P dot plus gamma P over M equals F of T. And what we want to know is and let's say we're in one dimension. Is that for this board or not? Yeah. Yeah, actually, vectorial asymmetry is my thing. So, I mean, sorry. So let's take this equation. Let's actually try to derive this in a slightly adult way. Okay? Derive what A must be. Let's rewrite this equation. We can rewrite it, I hope. Right? Everybody agree? And therefore, we know that P times e to the gamma t over m is equal to the integral up to t from some reference time of right? Let me write this way. Yes? Clear? Okay. So the reason we're doing this is, remember, how do you deal, remember I said, f is a random function. What do I mean by random function? It means that I reach into my bag and pull out a curve f. I plug that in here. I solve this equation of motion for that curve. Yes. Looks like I've started with 0, haven't I? Yes, yes. I'm sorry, no. I just left out the P of 0, that's all. So, excuse me. P of minus P of 0. Yeah, thank you. I mean, my worry is only that I want to try to write on the board what I have in my notes. I don't want to improvise. So thanks very much. And so now you can ask, what would you like to calculate? You'd actually like to calculate how this momentum or velocity is correlated in time. But step one, you'd like to calculate its value when the two times are the same. So let's calculate P of t, P of s for two different arguments t and s. Okay? Let me write this on this side. And remember, this is all being done, for the greater common good, because eventually what we want to do is to go away from this equilibrium problem. But in order to go, so we'll do it. Okay? All right. So let me write this slightly differently. Let me write P, therefore, is e to the minus gamma t over m here, and this guy here. Right? And therefore, P of t, P of s, I can write as this guy first. Make more room, excuse me. Of this stuff, right? Which is times e to the times exponential gamma over m t1 minus t exponential gamma over n t2 minus s. So that, and what does it mean? What this means is, if I want to calculate this quantity, Now, there are two ways of viewing it. One is what you really want to do is you can just run one thing for a long time in the noise. Hopefully, we'll explore all possible values. The other is imagine doing the experiment at this level, at the level of the calculation, what you're doing is you're actually saying I'm averaging over the probability distribution of the noise. Okay? So that's, at the moment, we just take it that way. We can then discuss what it means for a real experimental system. Okay. So if we do that, we use what we've been given here. A delta of t, right? Just to do a little bit of elementary algebra on this, and what you will get. And let's, without loss of generality, I always want to say that. Without loss of generality, let's take s greater than t. Okay. All right. Let me actually write this. So I'll put in for this guy a times delta of t1 minus t2, and I'll carefully do my integrals, and I assure you I will get I have changed notation. I called my noise 2D. So if you don't mind, just let's call it A. It's fine. Plus there should be an M somewhere. Where did all that come from? I'm mildly worried about my factors of gamma. Something looks not right. Just give me a second. I think my gamma should be downstairs, shouldn't it? That's an A. I'll get M over gamma. I'll get another M over gamma. Everything I want to get. So just give me a second while I that guy is fine. When I do my integral, let's actually do it. Let's put in one step. I've done some shady switch of notation in my notes. All right, let's actually do one of these. So this will be integral 0 to t dt1, integral 0 to t, integral 0 to s dt2, and then I'll have an a, and I have a delta of t1 minus t2, delta of t1 minus t2. So when I do that, if s is greater than t, then I said s is greater than t, right? Okay. So I'll get, so okay, first of all, this integral should give me what? It should give me, so I'm doing an integral from 0 to s dt2 delta of t1 minus t2. So this will give me non-zero only if t1 lies between 0 and s, right? And what that means is non-zero only if t is less than s. Right? Am I getting it right? Anyone following? Okay. All right. But since I've taken s greater than t, that's fine. So this will give me 1. That gives me 1. And it evaluates t, this was t, what did I call it? This is t1, t2. It evaluates t2 at t1, fine. So it will make this guy equal to t1. Am I still doing okay? I think I am. This guy, right? And so then I have e to the minus gamma over m, t plus s outside, times a, times the integral from 0 to t of e to the minus twice gamma over m t1 dt1. So anyway, now I think I will leave the rest of this doing the integral to you guys. Now, yeah, so I've done it for s bigger than, clearly if it's for t bigger than s, I'll get the opposite. So eventually what I will get, I'm missing an s somewhere. Oh, it's here, it's fine, yeah, okay. So eventually what you will get is will be this transient bit plus a m over gamma, m over 2 gamma, right? And I got it right? I think it's actually right. Yes? Miraculously. Okay. And notice that this, together with that, no, this is fine, this is fine. Now next, I'm just a little worried, but where is S gone? Oh, it's here. Thank you. Times e to the minus gamma. Do not cross. Okay. So eventually I'll get P of t. So for let t and s both go to infinity. So you forget the initial state that you've prepared, thereby getting rid of this term. And then what you'll get is P of t, P of s is, and now let's consider s greater than t as well as t greater than s. You'll get a gamma over m mod s minus t, and you have a coefficient which is m times m over gamma times a. And I'm just worrying about factors of 2. What I know is there should be a downstairs still, right? There still is a 2 there, and it's still there. Good, yeah. That's why you put 2D. No, but the thing is, I didn't want, it's just, hang on. I didn't want to call it a diffusivity because it was for momentum. Okay? All right. Okay, and now what we're going to say is, in particular, we want, for long times, after you've forgotten how you prepared it initially, you want average p squared over 2m to be half kbt. So you want this to be m kbt, right? Insist. And hopefully it'll all work out correctly. Let's just check. I'm sure something is going to go wrong. Let's see. So m So I've survived. Okay. All right. So, what have we learned from this? What we've learned is that if we insist on writing the dynamics of a particle in amidst a bunch of other particles kicking it around, if we assume that everybody is at thermal equilibrium, then this model turns out to be internally consistent with the idea of thermal equilibrium. Once you choose this to be a white noise, it turns out that all you have to do is to insist that this coefficient is 2 kBt times the friction. Okay? So this tells us, now immediately you can get the answer to the other problem we had here, namely this one. At least for the case I really want to reach into production. What is my just about? So now let's take another equally simple case. Supposing you take u of q to be a half kq squared. Okay, just so the calculation is completely mirrored, and you ignore inertia. Then immediately here you can see that you want 1 over gamma squared times f of 0, f of t to be equal to over that is to say this we said was a I got it right. Something is going wrong. Yeah, it's fine, yeah. In other words, the noise on the position coordinate being equal to twice the conventional diffusivity ensures that the probability of Q will be take my word for it, even when you have both a potential and inertia, the same thing works out. Okay, and it works out for arbitrary potentials because the derivation didn't really depend on it. Okay? All right, so now what I want to do, I guess probably what's going to happen is I'm barely going to be able to do Fokker-Plancle. Before going further, I want to make one more little point, which is, we've been talking about this noise and very casually saying, we know how to do it. It's this kind of object. What does that mean? Because, we're talking about a probability distribution on the space of functions f. Okay? So, physicists, of course, are accustomed to doing these things without really worrying too much about the underlying maths. But let's remind ourselves that we're actually doing fairly adult mathematics. Okay? Because what we're saying is that what does this really mean? What this means is the probability distribution for the function f is e to the minus, I claim, let me say this correctly, divided by a normalization. Now, I am not even going to try to write the normalization because obviously it's a little awkward. Okay? A way of thinking about this is to, so is this point clear to everybody? speak up or forever hold you, please. Okay, so, we were able to do formal manipulations with an object of this sort. But what this really means is we're talking about a distribution function on the space of functions f. Okay, so P is a functional. You give it a function, it gives you a probability density for that function, right? And it's a tricky object. And you understand what I mean by saying that I don't really know how to write down the normalization. If you want to make this object, so first of all, you should carry out exercise, check that this is true if this is true. Okay? But, you can reduce this to something completely familiar by undoing the work of centuries of mathematics and turning the integral into a Riemann sum. Okay, whatever. And then you just say this is e to the minus 1 over 4 kt. And there is some little time step, which I'll call epsilon. And there'll be a sum over values of f at various little times. Okay, so the idea is, all we really mean by this object is that, again, thinking one-dimensionally, here is, a typical graph of f of t. I'm sure I'll do it wrongly. No, that's wrong. That's the Brownian motion. Something like that, I don't know. Even that's probably wrong, right? Is that what a white noise looks like? I'm not very confident of drawing the right graph. But all I'm trying to say is the following, that when I say P of f, what I mean is this. At each time, I can draw a probability distribution. Okay, at a given time t, I can draw a probability distribution for f, right? At another time t, I've got another probability distribution for f. They're all the same distribution, and therefore my graph of f can pick a point here, a point there, a point there, anything. And that's why what I was drawing was wrong, because I didn't make it jump enough. Right? Okay. So this is what I mean. It's picking 2 points of the same. Yeah. Except then there is this other issue of the delta t, square root. Yeah. So, yeah, maybe I'll come to that. Okay? But even if you want to think about what you mean, think about this picture. You've got a Gaussian point, and you pick one option. So this is f. You pick this value, then you pick that value, and maybe you pick that value, and so forth. And that's what will be the time series of this graph. Okay? And clearly, if these were discrete points, and the function is identically and independently distributed at those points, the distribution is just a product of the Gaussian for f at each point. Okay? Then you make those points much closer and closer together, and it becomes this. So you don't need to fear it, but you need to know it. Okay? And the reason I want this is that we'll be calculating entropy productions, etc., using this. Okay. Okay. So. Yeah. So maybe I should do the delta t bit. That might be a reasonable place to stop also. We want to build the equation satisfied by P of xt, the probability density for being at x at time t. So let's do it for this case, okay? Now, let me use q as my random variable, and let me use x as the values it takes, okay? The probability that q has the value x at time t. So I've got q dot equals, neatly speak, borderline consistent from earlier notation. Where this is a white noise with that strength that we talked about. Okay, so then q of t plus delta t. We're going to figure out how to build this probably in the next lecture, but I'll do one key step right now. Let me call this bit, we just call it something. We just call it v of q. From t to t plus t. I mean, you could worry about whether I should do something like this here. You can check post facto that you don't need to. Okay? And what we want to ask, so then we know that, let's call this delta q. Then average delta q is clearly just delta t times v of q. However, how much is delta q squared going to be? And then we'll average it. It's going to be v squared of q, average, v squared of q, yeah, average, I guess, times delta t squared. Plus a cross term, but that cross term, okay, we'll see. Let's write them all down. Minus, right? I'm calling this v of q. So it becomes plus v times f. There'll be two of them, right? Right? And yes, I have to keep these 1 over gamma squareds. Yeah. Well, v reaches the value. So, I mean, then I have to actually say which calculus I'm using. Yeah. So, if I evaluate f at a time an instant after, then I get rid of this. So I have a delta t squared term. So yeah, I will have to make that point because I have a function of q times f. So what I really mean is this is going to be 0 because I'm evaluating f an infinitesimal instant after q. The f that you draw at the next instant doesn't know about your present value of q. So this guy is 0. And then I have this. And the curious thing is that this term, which seems to have 2 delta t's in it, and you might, if f had been a sensible function, this would have been a term of order delta t squared, right? Because I'm, looking at things at order delta t squared. This term is, of course, of order delta t. It is just, I just want to, so what did we agree that f was? F has 2, yeah. So this term ends up being 2d delta T. Which, of course, you kind of knew, because you know that if I take away the force, then that's what Q does. But the important thing is that you go apparently to second order to get an effect that's of order delta T. So this needs to be kept in mind. And what I'll do, I think, is this is a good place to stop. What we're going to do is the following. What we're going to do is the following. Let me just draw a picture. To build P, build the equation for P, we're going to say that, here is a history. Here is one possible history of X, of Q of T. Right? At a given time, here are some times. So T1, T2, T3, blah, blah, blah. In a given history, it intersects this once. Right? There's no antiparticles in first order stochastic calculus, so you don't have to worry about this intersecting it many times. Okay? And so what we will mean by the probability distribution of Q is you'll get a sort of mass of points here, right? As you repeat this many, many times. Right? In one history, it intersects once. Next time, it'll be there. So here's another history. There's another history. I can start them all from the same initial condition if you like. Right? And so what you want to do is use this picture to build how P evolves in time by saying that P would reach here from any of the points over here through a process given by the equations. And we'll do that. And the reason I'm dwelling on this is that eventually I want to use this sort of formalism to calculate entropy production. So I went over somewhat elementary ground, but yeah. So questions? Totally clear, totally snowed, totally bored. There's three possibilities actually. The snowed is different from bored and different from clear. Now you've already seen it and therefore you could teach it, or you've already seen it and you hope never to see it again, or already seen it and didn't mind seeing it. Again, there are three. There's three of many things. Yeah. No, seriously, already seen it and mastered it? I'm asking you, really, real question. And there's no, absolute, most of the stuff that I teach, I have not mastered in the sense that I have to go back to my notes before I teach it. We all do it all the time. So tell me, already seen it and kind of know it? No, then that's not kind of. You've done this kind of calculation means more than kind of know it. So you've done it. No, so meaning you could go up to the board and do it. That's true for all of us. Okay, all right. So fine. In the next lecture, about 2/3 of the next lecture, I will talk about entropy production of active particles. The last 1/3, I'll show you some